Good afternoon. I'm Bob Barbet, and I want to talk today a little bit about a little project we worked on, evaluating Refrac economic potential and primary infill relative well performance in the Permian organic shales. I'd like to acknowledge my co-authors, John Stroder and Mark Villarreal, for their help on this project. Some of the things we talk about today, basically we're trying to estimate recovery factors for refrac candidates using current best practice refrac designs, and of course using operator production. What a refrac's going to do as far as recovery factor, because you're ideally going to put an optimized refrac treatment on your well with best practices when you go to refrac it. So how does that compare to what you have right now to get your EUR for the refrac? Looking at recent completions with enough production data with close cluster spacing, high loadings, determine what your expected production increase is going to be from the optimized treatment. We had 196 wells and 36 open hole vertical well logs in the Midland Basin, Central and Southern Midland Basin. 39 of these wells had clear producing heights, and those are the ones that we use for our numbers and best practices at recovery factors. And individual well production was critical to this. A lot of consultants and service companies try to do these type of studies, and usually they don't come out very well. Well, this is the reason, because that's what they're dealing with is a noise. You just can't use public data, period. That's into discussion on that. There's no real justification for that. You're going to get the wrong numbers. Primary finding was that your close cluster spacing wells with high proppant and fluid loadings are starting to approximate solution gas drive reservoir numbers. 13.7 P50 number is right below the 15% number for matrix perm reservoirs. The theory is that as you're getting more and more of your drainage area stimulated, you're getting more and more permeability, more and more permeable area, and you're starting to basically emulate a matrix reservoir, because your perm is mechanical in an organic shale. It's not geological. I mean, it's primarily mechanical. There's some geological, but not much. So basically it's mechanical, so the more you mechanically alter that rock, the more you're going to be similar to a matrix reservoir. Can you be closer? Can you get higher numbers? Well, you're starting to get into stress shadowing issues. You start getting these clusters too close together. They've seen some issues in the Eagle Ford, and with the modulus in the Permian being higher, it's unlikely that you're going to get better there. It's actually going to have to spread them out even more, I think. So I think the 15 feet's kind of here to stay. We can play around with lower spacings, but it's going to be tough. This kind of validates what we're doing, or at least it's a cross-check using a completely separate methodology, using rate transient analysis, also using the dual porosity model, reservoir modeling. University of Lands did this study. There's this reference down there. The green dot is fairly close to where they're seeing on the close cluster spacing. The red dot, which with 10 refrac candidates with wider spacing, is pretty much following the trend as well. So I think this is pretty good. A good cross-reference. It also validates that our 330 drainage radius is probably not too far off, because you are starting to see numbers that approximate real values, the 15% number for solution gas, for instance. Okay, so does it mean that everything's right? Well, you could be canceling errors, but no, it's more than likely we're pretty close, and we got a fairly consistent basis for this. Here's an example from one of the HFTS wells. Again, with 50-foot cluster spacing, your predicted recovery factor is going to be about 6%. You're leaving about 60% of the stage not stimulated there. Primary infill, one of the problems you run into is you've got to have a good type curve. And where did that type curve come from? Well, did it come from optimized completions? Most of the time it doesn't. So, in that case, how do you know what you're losing? You have to have some kind of independent way to get that. So if you can eliminate the need for offset production, as far as saying, okay, well, this well made X and this well made Y, therefore Y divided by X is my reduction. Well, yeah, what if X was the wrong number to start with? So you've got to know what the best practices numbers are, and that's where this comes in. And we didn't have the optimized completions on a lot of these wells. That's why we had to use averages to get our P50s, to get our recovery factors. So you really don't know if it's a poor performer, whether it's from poor cluster efficiency or primary infill issues. And without auxiliary diversion, cluster efficiencies have been in the 59% range, according to Paul Weddle's work. And that's 85% for both diverter methods. So basically, you got to get away from using offset production if it's not optimized. And if it's optimized, that's another story, but most of the time it's not. So this provides an independent measurement to be able to go in and do this, benchmark these infill primary issues to show what the detriment is from asymmetric fracturing. What we did, 36 well logs, normalized data, calibrated to core. We mapped the individual layers. Not necessarily these weren't the properties that we used for the simulations, but we wanted to make sure there was geological continuity among the layers. We tried to keep all the producing wells within the perimeter of the open hole log control to be able to know that we've got reasonable properties on these. The height estimate we picked from Rock Properties. Bruce Meyer and I had a paper back in the 90s on that. Talks about that, how we come up with that, triple combo related Poisson's ratio, etc. Initial heights we picked manually using obvious stress layers, but then we went ahead and picked up Refrac towards the end of the project and used that on selected wells. Here's an example log with a tie to core. You can see pretty good agreement with the porosity on the right, pretty good agreement with the XRD on the left. Water saturation is good. The green curve is your stress profile. This one would not be a good example if we had a lateral in here because you've got a lot of barriers in here. We would not use this for calibration. On the other hand, this one would be a good example. We got pretty good strong barriers here and here, and you're looking at your yellow is probably your height through there. So that's what we used for an example. And again, this is Wolfcamp B, but the operator was mapping Wolfcamp B and says, hey, based on my Wolfcamp B, your numbers ought to be better. And I said, well, yeah, because you're not fracking your entire Wolfcamp B. Our numbers were actually pretty good. They were good everywhere else around the area, but where they had these barriers there, we were disconnecting with what the operator thought they should be producing. And he says, yeah, well, you're not producing the entire height. So a good example of that. The actual heights, it's all over the map here, from 84 to 84 average in the southern south, 116 in the north, as low as 45 in the south, as low as 50 in the north. The University Land Study assumed 200 feet. Where that's only really lower Spraberry shale where that occurs, I think. Here's an example Rock Properties plot. Here's the lateral. Here's the Rock Properties profile. We would have thought that would have been a good barrier, but Refrac says no. It's really going to go to there. Run the first pass at 6 barrels a minute, and this is where we recommend you start because that's a good critical rate, low-end critical rate to avoid screenouts. You can probably go lower for screenouts, but this is a good number. If you get an acceptable geometry with 6 barrels a minute, that's probably the way you want to go, and possibly with some HVFR. Because basically your rate per cluster is what determines how many clusters you can have, because your rate's going to be a finite number. 85 with expandable, 80 to 85, 100 barrel a minute on a new well. Your 6 barrels a minute is going to give you your number of clusters, and the more you get, the cheaper the completion is going to be. When you come up to 9 barrels a minute, you really don't see much of an increase in this particular case. So, if you can get the same geometry at 6 as you do at 9, and you can have fewer clusters with, more clusters per stage with 6 barrel a minute, then that's obvious you want to do that. What else can you do? Well, kick in some HVFR, and you get a little bit more height at the 9 barrel a minute. But overall, this exercise is good and to get you your height and also to see whether your 6 barrel a minute is going to work or not, which is going to be your most cost-effective rate. Drainage area assumptions, you got to assume an area. You got to normalize it to lateral length and use a reasonable width. Anecdotally, we saw about a 15% increase going from 330 to 440, so we know it's at least 330. We integrated RTA, and I say we, the University Lands people did. But again, the 220-foot drainage width from RTA assumed a 200-foot drainage height, so we're seeing less than that. We use 330, and basically, is that right? No, I think it's important for consistency. We did match the University Lands recovery factor numbers pretty well with our close cluster spacing number and our wide cluster spacing number, so it's certainly reasonable. Otherwise, you'd have a pretty big departure from that. But since your recoverable is going to be based on EUR per acre times the number of acres, the acres go within there. Your estimated recovery with the Refrac as a function of per acre, the more acres you have in there, the more it's going to be. I think it's the 330 is going to give you, I think, a conservative estimate of that. So, which is good. You want to under promise and over deliver on these situations if you can. The EFAs, we got a lot of pushback on this. $3 million average for these wells. They're relatively shallow, 6,700 feet, 8,000 feet. Basically, If you use XLE and expandables, you're going to get a 20% cost difference automatically from ones they're doing. And most of these operators in the area were doing the optimized completions with 10 clusters per stage, 150-foot cluster stage spacing. So basically you can go to a lot more than that. You can go to 14 with a refrac, 15 on a new well. And you knock that number down, and also you take a 15% savings with the industry conditions. You're down around the 3 million range. Operators in opposite areas were doing around 3.8 to 4. Well, that's 2019 using way too many stages. Here's a strip price. Read it and weep, but it is what it is. And we're using this for all our assumptions. Even with that, though, you got a pretty good rate of return. $26 million NPV10 for your 7-well refrac program here, versus 1.2 million current production. So you're not accelerating. You're getting new rock. We'll look at this number here a little bit later, the PV20. That comes in on your refrac PUD booking. But overall, pretty good. Really strong rate of return on 7 of the 10. So can you make refracs work at today's prices? According to this, you can. So the other thing, which is the big prize, and nobody's really taken advantage of this yet, but not because it's not something that'll work, just because nobody's taken advantage of it yet. You've got to have a clear indication that reserves are added and not accelerated to get bookable reserves from refracs. We showed that here at 1.2 million versus 46 million. There's no question that most of the numbers are going to be new production. Reasonable certainty refrac operation to be successful. That second criteria was a big if until recently, until about 2017, when people started mainstreaming the mechanical isolation. Results were all over the map. You really couldn't do this with the vertifracs. And then you want to generate a large enough number of successful refracs to establish confidence, and that we think is around 5 to 6 wells. And this is all put together by Denham Capital. That's where Samantha was working at the time. We also had Ryder Scott people in our presentations, and they agree that the process does make sense that we're looking at here. What the numbers mean? You're going to go from a 26 million NPV10 to 159 million present value. That's truly money for nothing, as they say in the song. It's saying not really nothing. You got to get a reserve report, but this is the potential here, especially in today's economic conditions. This is something that people need to really look at hard. For a $20 million investment, you're looking at this type of return. You're not going to see that anywhere on anything that you do out there. Some conclusions. We're finding that, as you start getting your clusters closer and closer together, with the high loadings, you're starting to emulate conventional reservoirs. You've got a constraint there at 15%. You haven't seen much more than that in solution gas drive. That's probably the cap here. 13.7 is what we're using. And it gives you a means to quantify the expected increase in productivity for a refrac, providing that you maximize your cluster efficiency with XLE. You can also do it with diverter, but XLE is a lot cleaner, a lot more efficient, and got a lot more benefits to it. The initial benefit is if you've got some good solid number for what you should be getting out of these, you no longer have to use offset analog wells for type curves to try and see what your performance degradation is for primary infill interactions, or even just any kind of process, like using diversion or using different types of completions techniques and whatever. You can use this number now. You don't have to have an optimized offset, which you rarely do have. You will have this number all the time, but you will rarely have an offset that's optimized. So basically what this suggests is that you can make refracs economic even in the current poor pricing environment on a cash-by-cash basis, straight up investment type deal. But when you start looking at booking reserve behind pipe, this can be off the charts. So, and what we can see is with the use of mechanical isolation, you get a lot more consistent results. And to make this work, though, you have to have the maximum cluster efficiency possible at the lowest possible completion cost. It's all economics. If you can do it much cheaper, then you want to. If you use something other than XLE, if you use something other than expandable liners, it's not going to work. It's going to work a lot less better. It's going to be hard to make it work. Anyway, but that's all I've got for now. Let's open it up for questions.